Non-metallic cable would be an acceptable wiring method for this building as per the National Electrical Code. Non-metallic cable is a type of electrical cable that is commonly used for residential and commercial wiring. It is composed of two or more insulated conductors that are wrapped in a non-metallic sheath. Non-metallic cable is typically used for branch circuits, which are the circuits that provide power to outlets and lighting fixtures. When using non-metallic cable, there are a few things to keep in mind. Firstly, non-metallic cable must be installed in accordance with the National Electrical Code. Secondly, non-metallic cable must be protected from physical damage. Thirdly, non-metallic cable cannot be used in wet or damp locations. In this case, the building is a single-story wooden frame structure with no attic access. This means that the non-metallic cable will be installed in a dry location and will be protected from physical damage. Therefore, non-metallic cable would be an acceptable wiring method for this building. The National Electrical Code provides comprehensive guidelines for the safe and effective installation of electrical systems, including the use of non-metallic cable. Some key aspects to consider when installing non-metallic cable are ampacity, support, and protection. Ampacity refers to the current carrying capacity of the conductor within the cable. The National Electrical Code specifies the allowable ampacity for various sizes of conductors, and it's crucial to select a cable with an ampacity rating that is sufficient for the intended load. Factors such as ambient temperature and the number of current carrying conductors in a raceway or cable assembly can affect the ampacity. The National Electrical Code provides tables and adjustment factors to account for these variables. Support of non-metallic cable is also critical. The cable must be securely fastened to the building structure at appropriate intervals to prevent strain on the conductors and terminations. The National Electrical Code specifies the maximum spacing between supports for non-metallic cable. Proper support ensures that the cable is not subjected to excessive tension or bending, which could damage the insulation or conductors. Protection from physical damage is another essential consideration. Non-metallic cable is relatively vulnerable to damage from impacts, abrasion, and other mechanical stresses. The National Electrical Code requires that non-metallic cable be protected where it is exposed to physical damage. This protection can be achieved through various means, such as installing the cable in conduit, using gauze strips, or locating the cable in areas where it is not likely to be damaged. In addition to these general requirements, there are also specific rules for installing non-metallic cable in different types of buildings and occupancies. For example, the National Electrical Code has special provisions for installing non-metallic cable in damp or wet locations, in hazardous locations, and in fire-rated assemblies. It is important to consult the National Electrical Code for the specific requirements that apply to the particular installation. Grounding is also a critical aspect of electrical safety. The National Electrical Code requires that all metal enclosures and equipment be properly grounded to provide a path for fault current to return to the source. This helps to prevent electrical shock and minimize the risk of fire. Grounding can be achieved by connecting the metal enclosures and equipment to a grounding electrode system, such as a ground rod or a metal water pipe. Overcurrent protection is another essential safety feature. Overcurrent protection devices, such as circuit breakers and fuses, are designed to interrupt the flow of current in the event of a short circuit or overload. The National Electrical Code specifies the maximum allowable overcurrent protection for various sizes of conductors and equipment. Proper overcurrent protection helps to prevent damage to the electrical system and minimize the risk of fire. Wiring methods refer to the different types of cables, conduits, and raceways that can be used to install electrical wiring. The National Electrical Code specifies the allowable wiring methods for different types of buildings and occupancies. Some common wiring methods include non-metallic cable, metal-clad cable, electrical metallic tubing, and rigid metal conduit. Each wiring method has its own advantages and disadvantages, and the selection of the appropriate wiring method depends on the specific application. Electrical boxes are used to enclose electrical connections and provide a safe and convenient way to access the wiring. The National Electrical Code specifies the types of electrical boxes that can be used in different locations and the requirements for installing them. Electrical boxes must be securely mounted and properly grounded to ensure electrical safety. Conductors are the wires that carry electrical current. The National Electrical Code specifies the types of conductors that can be used in different applications and the requirements for installing them. Conductors must be properly insulated and sized to carry the intended load. Terminations are the points where conductors are connected to electrical devices, such as outlets, switches, and circuit breakers. The National Electrical Code specifies the requirements for making electrical terminations. Terminations must be made in a secure and reliable manner to prevent loose connections, which can cause overheating and electrical hazards. Lighting fixtures are used to provide illumination. The National Electrical Code specifies the requirements for installing lighting fixtures, including the type of fixtures that can be used in different locations and the requirements for supporting and grounding them. Outlets are used to provide a convenient source of electrical power. The National Electrical Code specifies the requirements for installing outlets, including the type of outlets that can be used in different locations and the requirements for grounding them. Switches are used to control lighting fixtures and other electrical devices. The National Electrical Code specifies the requirements for installing switches, including the type of switches that can be used in different locations and the requirements for grounding them. Electrical panels are used to distribute electrical power to different circuits. The National Electrical Code specifies the requirements for installing electrical panels, including the type of panels that can be used in different locations and the requirements for grounding them. Ground fault circuit interrupters, also known as ground fault circuit interrupters, are used to protect people from electrical shock. Ground fault circuit interrupters are designed to detect ground faults, which occur when electrical current leaks to ground. When a ground fault is detected, the ground fault circuit interrupter quickly interrupts the flow of current, preventing electrical shock. The National Electrical Code requires that ground fault circuit interrupters be installed in certain locations such as bathrooms, kitchens, and outdoor areas. Arc fault circuit interrupters are used to protect against electrical fires. Arc fault circuit interrupters are designed to detect arc faults, which are dangerous electrical arcs that can occur in damaged or deteriorated wiring. When an arc fault is detected, the arc fault circuit interrupter quickly interrupts the flow of current, preventing electrical fires. The National Electrical Code requires that arc fault circuit interrupters be installed in certain locations, such as bedrooms and living rooms. Surge protection devices are used to protect electrical equipment from voltage surges. Voltage surges are sudden increases in voltage that can damage or destroy sensitive electronic equipment. Surge protection devices are designed to absorb or divert voltage surges, protecting the equipment from damage. The National Electrical Code recommends that surge protection devices be installed in all buildings. Electrical inspections are conducted to ensure that electrical installations comply with the National Electrical Code and other applicable codes and standards. Electrical inspections are typically performed by a qualified electrical inspector. The electrical inspector will examine the electrical installation to identify any defects or violations. If any defects or violations are found, the electrical inspector will require that they be corrected. Electrical safety is a critical concern. Electrical shock can cause serious injury or death. Electrical fires can cause significant property damage and loss of life. It is essential to follow all applicable electrical codes and standards to ensure electrical safety. Only qualified electricians should perform electrical work. If you are not a qualified electrician, you should not attempt to perform electrical work. Always turn off the power before working on electrical circuits. Use caution when working around electricity. If you are not sure how to do something safely, ask a qualified electrician for help. The National Electrical Code is updated every 3 years. It is important to stay up to date on the latest requirements of the National Electrical Code to ensure electrical safety. The National Electrical Code is a complex document. If you have any questions about the National Electrical Code, consult a qualified electrician or electrical inspector. Understanding conductor types is crucial. Conductors are the pathways for electrical current, and the National Electrical Code specifies the type suitable for different applications. Copper and aluminum are the most common conductor materials, each with distinct properties. Copper offers superior conductivity and corrosion resistance, but is more expensive. Aluminum is lighter and more cost-effective, but requires larger sizes for equivalent ampacity and specific termination techniques to prevent oxidation. Insulation is another key factor. Thermoplastic high-heat resistant nylon-coated, cross-linked polyethylene, and rubber are common insulation materials, each rated for different temperature and environmental conditions. The National Electrical Code designates conductor types with letter codes like THHN, THWN, and XHHW, indicating their insulation properties and suitability for wet, dry, or high-temperature environments. Selecting the correct conductor type ensures safe and reliable operation. Understanding ampacity is also essential. Ampacity refers to the current carrying capacity of a conductor, measured in ounce. The National Electrical Code provides ampacity tables based on conductor size, insulation type, and installation conditions. Factors like ambient temperature, the number of conductors in a raceway, and the presence of thermal insulation can affect ampacity. Dating factors are applied to reduce the allowable ampacity to prevent overheating and insulation damage. Proper ampacity calculations are crucial for preventing fires and ensuring the electrical system operates within safe limits. Overcurrent protection is vital for safety. Overcurrent protection devices such as circuit breakers and fuses protect electrical circuits from excessive current that can cause overheating and fires. Circuit breakers are resettable devices that trip when the current exceeds a predetermined level, while fuses are one-time devices that melt and interrupt the circuit. The National Electrical Code specifies the maximum overcurrent protection for different conductor sizes and equipment. Selecting the correct overcurrent protection device ensures that the circuit is protected from damage or potential hazards. Grounding and bonding are critical safety measures. Grounding provides a path for fault current to return to the source, minimizing the risk of electrical shock. Bonding connects metal parts of the electrical system to create a low impedance path for fault current. The National Electrical Code requires grounding and bonding to be installed in accordance with specific requirements to ensure electrical safety. A grounding electrode system, typically consisting of a ground rod or metal water pipe, provides a connection to earth. Proper grounding and bonding are essential for protecting people and equipment from electrical hazards. Understanding wiring methods is crucial for safe and compliant installations. Wiring methods refer to the different ways electrical conductors are installed, including cables, conduits, and raceways. Non-metallic cable, metal-clad cable, electrical metallic tubing, and rigid metal conduit are common wiring methods. Each method has its own advantages and disadvantages, and the National Electrical Code specifies the allowable wiring methods for different applications. Factors like environmental conditions, physical protection requirements, and building type influence the selection of the appropriate wiring method. Proper installation of wiring methods ensures that the electrical system is safe, reliable, and compliant with the National Electrical Code. Understanding voltage drop is important for efficient operation. Voltage drop refers to the reduction in voltage along a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction, reduce lighting brightness, and increase energy consumption. The National Electrical Code recommends limiting voltage drop to a maximum of 3% for branch circuits and 5% for feeders. Voltage drop calculations are necessary to ensure that the conductors are properly sized to minimize voltage drop and maintain efficient operation. Selecting the correct conductor size and minimizing circuit length can help to reduce voltage drop. Furthermore, understanding grounding electrode systems is vital. A grounding electrode system provides a connection to earth, ensuring a low impedance path for fault current. The National Electrical Code specifies the requirements for grounding electrode systems, including the types of electrodes that can be used and the methods for installing them. Ground rods, metal water pipes, and concrete encased electrodes are common grounding electrodes. The grounding electrode system must be properly sized and installed to provide effective grounding and protect against electrical shock. Regular inspection and maintenance of the grounding electrode system are essential to ensure its continued effectiveness. Also, understanding bonding and equipment grounding is crucial. Bonding connects metal parts of the electrical system to create a low impedance path for fault current, while equipment grounding connects non-current carrying metal parts to ground. The National Electrical Code requires bonding and equipment grounding to be installed in accordance with specific requirements to ensure electrical safety. Bonding jumpers are used to connect metal enclosures, raceways, and equipment to the grounding system. Proper bonding and equipment grounding are essential for protecting people and equipment from electrical hazards. Regular inspection and maintenance of the bonding and equipment grounding system are essential to ensure its continued effectiveness. In addition, understanding overcurrent protection devices is necessary. Overcurrent protection devices, such as circuit breakers and fuses, protect electrical circuits from excessive current that can cause overheating and fires. Circuit breakers are resettable devices that trip when the current exceeds a predetermined level, while fuses are one-time devices that melt and interrupt the circuit. A National Electrical Code specifies the maximum overcurrent protection for different conductor sizes and equipment. Selecting the correct overcurrent protection device ensures that the circuit is protected from damage and potential hazards. Regular testing and maintenance of overcurrent protection devices are essential to ensure their continued effectiveness. Finally, understanding surge protection is helpful. Surge protection devices protect electrical equipment from voltage surges, which are sudden increases in voltage that can damage or destroy sensitive electronic equipment. Surge protection devices are designed to absorb or divert voltage surges, protecting the equipment from damage. The National Electrical Code recommends that surge protection devices be installed in all buildings. Surge protection devices should be installed at the service entrance and at individual equipment locations. Regular inspection and maintenance of surge protection devices are essential to ensure their continued effectiveness.